to decrease in the value of activation energy, higher number of substrate molecule or reactant molecules get achieve the threshold energy level and get converted into the product. Next, we have also discussed the classification of enzymes. So basically, it was the EC classification. We have already discussed this EC classification. Okay, so this EC classification is the Enzyme Commission classification. According to this Enzyme Commission classification, enzymes are categorized in 6 groups. First group having the enzyme oxidoreductase. Second group having the enzyme transferase. Third group having the enzyme hydrolysis. Fourth group having the enzyme isomerases. Fifth group having the enzyme lysases. And sixth group having the enzyme ligases. And as I have already mentioned in last class, the order of these enzymes or these groups should be fixed. We should not shuffle the order. Okay. Then we have discussed the structure of enzyme. So basically, enzymes are protein. There is only one exception. There is one enzyme known as ribozyme, which is nucleic acid in nature. Or beside this ribozyme, all other enzymes are sorry, proteinous in nature. So if we have to summarize this structure, it has same structure as the structure of protein. As we know, in the structure of protein, we have 4 levels of structure. It is known as primary structure, secondary structure, tertiary structure, and quaternary structure. Primary structure is the simple linear chain of amino acids bonded by peptide bonds. And when this linear chain get folded into alpha helix or beta pleated sheet, it is known as secondary structure. And this folding is mainly due to formation of hydrogen bond. Third level of structure is the tertiary structure. Basically, this tertiary structure is the refolding of the secondary structure molecule through the various type of disulfide linkage, maybe van der Waal interaction, hydrophobic interaction. And fourth level of structure is the quaternary structure. In quaternary structure, basically there is a association of 2 or more tertiary structure proteins. Suppose this is the first and this is the second. So these are the association of 2 tertiary structure protein. Or in this more than 2 tertiary structure protein may also be present. So this is the quaternary structure. When the quaternary structure is present in any enzyme, it is known as oligomeric enzymes. Oligomeric enzymes. And if only this is structure having the only tertiary structure level, then it is known as monomeric enzyme. Monomeric enzyme. Okay, so basically in the structure of enzyme, as we know, in this structure there are some proteinous component, and in some enzyme beside this proteinous component, non-protein part may also be present. So this non-protein part is known as cofactor. Okay, and this protein part is known as apoenzyme. Apoenzyme. And generally this apoenzyme is inactive form of the enzyme, and when this cofactor get combined, it form the active enzyme. So this complete is known as holoenzyme. So basically holoenzyme is the combination of protein and non-protein part. Now this is the cofactor. So in this structure you can see this is the protein portion of the enzyme, this is the protein portion of the enzyme, and it is inactive. Okay, when a non-protein portion, generally known as cofactor, is get attached with this protein portion, they get converted. There is some conformational change, and the enzyme become active. And this active form of enzyme is known as holoenzyme. Okay, this is known as holoenzyme, and without the cofactor, it is termed as apoenzymes. This cofactor may be either metal ions or some organic group. Okay, So this is organic molecules, they are known as coenzymes, and metal ions, and the basic function of this metal ion to act as a bridge atom. Okay, so they bridge enzymes and substrate together, and combined with the protein, it is as catalyst. And coenzymes, non-protein organic complex. So these are the cofactor, and cofactor is essential for the proper activity of the enzyme. Okay. Now next is the mode of action of enzymes. How enzyme interact with the substrate. So for this, we have few hypotheses. So this hypothesis is known as lock and key hypothesis. And this lock and key hypothesis was proposed by a scientist, Fisher. Fisher proposed the lock and key hypothesis. Basically, this hypothesis explained the mode of interaction or nature of interaction between the substrate and enzyme molecules. And as name suggests, lock and key hypothesis. According to this hypothesis, enzymes were considered as a lock and substrate were considered as a key. And as we know, every lock having a particular key, and they can only be opened through a particular key. In the same way, every enzyme can only interact with its particular substrate. And then there is a formation of enzyme substrate complex like this. Then there is a formation of enzyme substrate complex, and then it may get converted into free enzyme and product. So this hypothesis resembles the lock and key analogy. So termed as the lock and key hypothesis. So here you can say this is the substrate and the enzyme having these complementary binding sites or active sites for the substrate. Now when the substrate get fit or get attached with the active sites, then there is a formation of enzyme substrate complex. And after this formation, it may get converted into free enzyme and product molecules. According to this hypothesis, the one important things, the enzymes were considered as rigid molecules. So in this, according to this hypothesis, enzymes were considered as rigid molecules, but later on it was found out that the enzymes are flexible molecules. But this Fisher considered the enzymes are rigid molecules, as in lock there is a permanent binding sites or complementary sites for the key. In the same way, enzymes having a permanent site or active site for the binding of substrate. But later on, it was found out that there is no permanent binding sites, and enzymes are flexible. When there is an interaction with the substrate and enzyme, this active site get appeared. But according to this lock and key hypothesis, the enzymes are rigid molecules and they have permanent binding site for the substrate molecules. Means there is no any conformational change during the interaction with the substrate molecule. It was the lock and key hypothesis. Second important hypothesis is known as induced fit hypothesis. And this hypothesis was proposed by Cousland. Okay, so Cousland was the enzyme who proposed the induced fit hypothesis. As name suggests, induce and then fit. Basically, in this, according to this hypothesis, enzymes were considered as flexible molecules. Means there is no permanent binding sites or active sites for the substrate. But when there is an interaction, when substrate approaches toward the enzyme, there is an interaction with the enzyme, and due to this interaction, the active sites get appear over the surface of enzyme, and with these active sites, the substrate molecule get attached. So this is the induced fit. Means the substrate induces the conformational change in the enzyme, and after this induction, there is a formation of complementary site or active sites or appearance of active site over the surface of enzyme, and then the substrate molecule bind with it, and then there is a formation of, this is the enzyme substrate complex, and finally they get converted into free enzyme and product molecule. It was the induced hit hypothesis. Okay, next is the enzyme kinetics. Enzyme kinetics. This is known as Michaelis Menten kinetics. Okay, given by Michaelis and Menten. Okay. So according to this Michaelis Menten kinetics, previously we have to derive the we have to derive the mathematical form of this Michaelis Menten kinetics. But now we have only the mathematical formula, so there is no need of derivation. So mathematically, this kinetics may be explained as like this. So this is the V naught. V naught is the rate of reaction, or we can say the speed of reaction. The term Vmax. Vmax is the maximum velocity, maximum speed, or maximum rate of conversion of substrate into the product. S is the substrate concentration, and Km is known as Michaelis Menten constant. Okay, so Km is known as Michaelis Menten constant. So when we plot this mathematical model or this equation, this equation is known as equation for the Michaelis Menten kinetics. We have the graph like this. Okay, so at one point we have the maximum velocity of enzyme catalyzed reaction. So this is known as Vmax, and half of the Vmax, if we find out the value on the x-axis, this is the x-axis, and here we have the y-axis. If we find out the corresponding value on the substrate axis at the half of the Vmax, so this value is numerically equal to the Km value, Michaelis Menten constant. So this Km value is nothing but it is the substrate concentration at the half of the Vmax. So it is that substrate concentration at which the rate of enzyme catalyzed reaction will be half of the maximum rate of the reaction. Okay. Now this unit of Km is the unit of substrate. Since it is on the substrate axis, so unit is the same as the mole per liter, or we can also write molar. Okay, it has the same unit as the unit of substrate. Never confuse, because name is the Michaelis Menten constant. Okay, so sometimes student write it has no any unit, but there are number of constant which has the unit. Okay, and one more important thing about the Km, this Km value also indicate the affinity of substrate with enzyme. Means what is the degree of affinity of the substrate with the enzymes. When we write Km value higher, or we can write the lower Km value. Lower Km value means higher affinity of enzyme with the substrate, while higher Km value indicates the lower affinity, just reverse. Okay, so if any enzyme having the higher Km value, it means it has the very less affinity or lower affinity with the substrate molecules. And if we represent the lower Km value of enzymes, so it means the enzyme having the very higher affinity for the substrate. Generally, for the practical purpose, we are selecting the enzymes with the lower Km value, because if it has a lower Km value, it will have the higher affinity for the substrate, and it will bind more number of substrate, and then consequently there is a formation of higher amount of product. Okay, so this is the significance of Km value, and Vmax is the maximum velocity of the enzyme catalyzed reaction. As you can say, this plot is the non-linear plot. So if we summarize this plot, there you can find the below this Km value, we have the first order reaction, and here we have the zero order reaction at the Vmax, and between this we have the mixed order reaction. So if we have to interpret, we have to perform the experiment, we are generally performing the experiment below this Km value level, because in this region we have the linear relationship between the rate of reaction and substrate concentration. So it is very easy to interpret the consequences. But at the higher concentration, it is the non-linear relationship. But to get the more information, we can convert this non-linear equation into the linear form. We can convert this non-linear equation into the linear form. So linear form of this equation is known as Lineweaver-Burke plot. This is nothing but this is the linear form of the Michaelis-Menten equation. Suppose if we write the Michaelis-Menten equation like this, hello, हाँ sir. Okay, so if we write the Michaelis-Menten equation and take the reciprocal of this equation, then we have expression like this. Reciprocal of 1 by V naught is the V naught. Now just reverse it. It is the Km by V max into 1 by F plus 1 by V max. Now this is the linear form of the equation. Here it is, this is the nothing but linear equation for the straight line. So if we plot this x value and this y value, so this is the x value 1 by s and this is the y value, then we have a linear graph, and this is the slope. This Km by Vmax, this Km by Vmax is the slope of the plot, and 1 by Vmax is the intercept of the y-axis. So 1 by Vmax is the intercept of the y-axis, and if we extrapolate this graph, then it will cut on the x-axis, and this value will give you 1 by Km. Since it is the negative coordinate, so we put negative sign here. So this is the linear form of the Michaelis-Menten equation and known as the linear plot or Lineweaver-Burke plot, and this is the more informative in comparison to the non-linear plot. Okay, so next topic is the enzyme inhibition. So basically enzyme inhibition is the decrease in rate of enzyme catalyzed reaction. Okay, so the basically inhibition is the decrease in the lowering down in the rate of enzyme catalyzed reaction. So there are number of molecules known as enzyme inhibitors, which when bind with the enzyme, when they interact with the enzyme, they lower down the or they reduce the rate of the enzyme catalyzed reaction. So this is known as enzyme inhibitors, and process is known as enzyme inhibition. So if we try to categorize this inhibition, it may be categorized as allosteric inhibition, reversible inhibitors, and reversible and irreversible inhibitors. So basically, these reversible inhibitors are those inhibitors which are temporarily bind with the enzymes, and through the dialysis we can remove the inhibitor molecules. But in irreversible, there is no such, we cannot remove the inhibitor, and the enzyme is enter into a dead complex and known as suicide inhibitors. The enzyme is no more functional and become non-functional enzymes. And there is one more types of inhibitor known as allosteric inhibitors, because on the surface of enzymes there are two sites. There are number of sites. Suppose if we take this site as a active sites, so there is some other sites over the enzymes which is known as allosteric sites. Basically, so suppose the substrate molecule bind with this site. This is the site for the binding of substrate. So this site is known as allosteric site. Allosteric site. So this site is the active site. Okay. So beside this active site, there is some other pocket or binding site over the enzyme, which is known as allosteric sites. And suppose if any inhibitor molecule bind with this allosteric site, it can regulate the enzymatic activity. It may either increase or decrease the enzymatic activity through the conformational change in the enzyme. So this is known as allosteric inhibition. But among these reversible inhibition, these three are very important: competitive, non-competitive, and uncompetitive enzymes. So now we will discuss the difference between these three types: competitive, non-competitive, and uncompetitive enzyme. First is the competitive inhibition. As name suggests, there is a competition. Means in on the surface of enzyme, suppose this is the suppose this is the enzyme. Okay, and this is the active sites present over the enzyme. Now from this active site, suppose this is the substrate. This is the substrate which can bind with this active sites. Okay. But if we take any inhibitor which has some similarity with the enzymes like this, some similarity with the enzymes, it can also bind with same active sites. So basically here, this is the inhibitor. Basically in this case, there is a competition between the substrate and inhibitor molecule for the same binding sites or for the same active site. So such type of inhibition is known as competitive inhibition. So basically in competitive inhibition, there is a competition between the substrate and inhibitor molecule for the same binding sites. It can be represented like this. Suppose this is the enzyme, this is the substrate, and from the same enzyme at the same binding site, inhibitor can also bind. If there is a natural phenomena, normal phenomena, if only substrate bind, it will form the enzyme substrate complex and that get converted into the enzyme and product. Okay, K1 is the rate of formation of ES complex and K2 is the rate of formation of product. And the rate of dissociation is of ES into the free enzyme and substrate is the K minus 1. Now suppose if instead of binding of substrate, the inhibitor gets succeeded to bind with the sites, active sites. So it will form a EI complex and it cannot be converted into the free enzyme plus product. So it will not give the product. So we can say this is the a dead end product which cannot be converted into the product. The such type of inhibition is known as competitive inhibition. Next type is the uncompetitive inhibition. So in uncompetitive inhibition, suppose this is the enzyme, and the substrate bind with the enzyme. There is an enzyme substrate, it form enzyme substrate complex. Then inhibitor, then inhibitor, then inhibitor also bind. Some inhibitor may also bind with this enzyme substrate complex. This is the substrate, this is the enzyme, and form the dead end product. So in this case, after the formation of enzyme substrate complex, there is a appearance of some binding site for the inhibitor. So by this inhibitor can bind and form the enzyme substrate complex, or ESI, enzyme substrate inhibitor complex, and this is the dead end complex. Dead end complex means it cannot be converted into product. But if there is no binding of inhibitor, it can convert into the free enzyme and product. Such type of inhibition is known as uncompetitive inhibition. So basically in uncompetitive inhibition, inhibitor bind with the enzyme substrate complex. Third type is the non-competitive inhibition. Okay. So in non-competitive inhibition, suppose this is the structure of enzyme. This is the enzyme and it has site. This site is for the binding of substrate and this is the site for the binding of inhibitor. Okay. So basically in non-competitive inhibition, there are separate site for the binding of substrate and inhibitor. So after the binding of this inhibitor, with the enzyme, there is a formation of enzyme inhibitor complex. Now after this binding, there is a change in the conformation. There is a structural change in the enzyme. So due to this change in the structure, now this active site for the substrate is no more available for the binding. Okay, so it will, although it will form, attach the substrate and form the dead end complex. Okay, or in the same way, this inhibitor can also bind with the enzyme substrate complex. Okay, and after the binding of inhibitor, again there is a formation of dead end complex. If there is no binding of inhibitors, it can convert into the enzyme and product. So this is the non-competitive inhibition. In uncompetitive inhibition, the inhibitor can only bind with the enzyme substrate complex. But in case of non-competitive inhibition, inhibitor can bind either with the free enzyme or with the enzyme substrate complex. Okay, so this is a graphical representation of all these three inhibition process. So this is the first one is the, this one is the competitive, this is the uncompetitive, this is the non-competitive. So basically in uncompetitive inhibition, Km value increase and Vmax value remain unaffected. So graph will be like this. This is the value for the Vmax. So they intersect at the same point, so they have the same Vmax value. But here you can notice the change in the Km value. This is the plot for the enzyme catalyzed reaction without the inhibitor, and this is for the with the inhibitor. While in uncompetitive inhibition, Km value reduce and Vmax value also get reduced. So it has the parallel graph. This plot indicate the uh, in absence of inhibitor, while this is the in presence of inhibitor. And in non-competitive inhibition, Km value remain unaffected and Vmax value reduced. So it has the same intersect at the y-axis, so same Km value, but there is a okay. So Km value unaffected and Vmax value get reduced. Okay. So this is the different types of enzyme inhibitor or enzyme inhibition. So it was all about the module 3. Okay. So in module 3 we have only these things about the enzymes, structure of enzymes, different mode of action of enzymes, lock and key hypothesis, induced fit hypothesis, as well as the enzyme classification, structure of enzyme, and enzyme inhibition. So this is enough for your module 3. In next day we will start the module 4 and then module 5. Just wait for the few minutes. I am downloading the attendance.